It's been a big few months for us, and by us I don't mean just John and the people here today, Matt, but also there's been a team of people behind this project delivering our 10th mini-conf. Wow. So first that's Josh. He's working on a couple of early self-driving cars we've been working on. He's been doing a lot of AI for us. Up in there somewhere. This is part of a Shenzhen tour that runs each year. So that gentleman in the lurid shirt on the left of the glass, that's Cameron Leeson. He tirelessly negotiated with Chinese factories in Shenzhen to get this RC car, and also pushed very hard to try and turn around our Plan A electronics.
Yeah, so that was there are two distinct things. The chassis was a big effort for him to get, and the electronics was from a totally different supplier. So the chassis, all sorted. The electronics, not so much.
So it's Andrew who's in the foreground. He did all the mechanical design around the core flute and the acrylic, and it just looks like just a couple pieces of core flute cut. But there's been a lot of effort in terms of making it strong and robust, and in ways that I can't even imagine. He's that.
Just a little anecdote on that.
Sure.
About a week ago, Andy and I were at the hackerspace, and we were working on part of the design. I can't remember quite what. We were experimenting with things, and the camera angle wasn't quite right, and Andy commented about it. And about 10 minutes later, a new bracket was handed to us, which put the angle just right, and we popped in and like, oh, it's perfect. So the design was sort of iterating right in front of us while we were busy doing something else. So he put a huge amount of work into it.
That's in the glass. That's Mark Wolf, who's done a lot of the AI work and a lot of underlying work behind the donkey car code. And that was all of us, I think, just a couple of nights before we left. So there's Andrew again, Matt, who's been amazing. Sort of came all this way just to help us with this workshop. John Spencer Middle, who did the design of the Plan A electronics, and two other dodgy characters on the right. Yeah, and that's Mark again. So I've also got a lot of help from sponsorship. So I think there's a little AI startup who are doing farm bots, helping out, and the company I work for, Silverpond, very helpful with the community. So I guess I want to give you the idea of over 10 years we've received so much help from people, and all the attendees like yourselves. It's been fantastic. So that was something I wanted to just call out at the start of before I ramble on about software. So yeah, so thanks everyone. And yeah, and also all the LCA organisers who year after year sort of trust that we'll turn up with something, and Linux Australia as well. So it's been pretty fantastic. So software. We end up with some instructions. So hopefully everyone's been able to build it, well, not this car, but something very close to it. And our aim was hopefully today, but definitely by the end of the week, that your cars are driving around. And one thing I got out of today was how much everyone contributes. So we've got some half-baked instructions, and many people contributed fixes and stuff on the fly, which is great. And one that was Alistair mentioned was, which I completely missed, was that we've actually the Raspberry Pi micro SD card is complete with self-trained models on there. So once your car's built, you can start having it run around at track self-driving. So before you go all to the effort of training. So that's sort of thing I'd like to encourage is once your car's built, is to immediately get it self-driving, so the goal's achieved, and then go into training and all that stuff yourself. Just to sort of mention that. So the software instructions, basically, it comes in several parts. Basically, it's getting the donkey car image onto the Raspberry Pi SD card, which we basically have done for you, but there's still instructions there to show you how that was done, which is basically a lot of pip installing of AI frameworks like TensorFlow, the Raspberry Pi camera, and the PWM driver. So it's just that basic software there. Then there's you clone the donkey car repository, and then you just basically get it to create a car. So there's that step of software configuration. But then there's also driving the car, acquiring training data, training the model, and then driving with the AI and control. So that's what I'll try and go through a bit now. So that's that overview. So basically, the car's complete. The trickier part is having to install the training framework on your own laptop, and so that's this first part. And so the Python world, like most scripting languages, pretty love-hate relationship with their package managers and the use of virtual environments. As the first step is get a virtual environment up to install a donkey car and TensorFlow into, so you don't pollute your system. So that's the first part. The key part here is you clone the donkey car repository. That's all the Python code that contains the neural network, and after that you're basically good to go. The installation of the software on the Raspberry Pi is, once again, it's a lot of underlying packages. That we use Mosquito to basically help find the IP address when it comes up, because there's a bunch of cars and a bunch of LCA subnets, and it's pretty hard to find your IP address. So we used Mosquito to publish that to the network, make it easy to find.
Just to clarify,
sorry.
That's using MQTT. So is everybody familiar with MQTT? Yeah, people have heard of it? Well, it looks like there are a few who haven't. So just to clarify, that's a publish-subscribe mechanism whereby devices can send messages to a central broker, and then other devices can see those messages. So it's fantastic for IoT applications where you have multiple discrete systems that need to be able to talk to each other. So that's what Mosquito is for. Mosquito is just a software client and server for implementing MQTT.
Cool. So then we get down to, there's a bunch of just Python and Fortran and other sort of HD5 or Python file format, just a bunch of utility things there. The first interesting one for us is installation of I2C tools, and you can use I2C to detect the PWM driver. So it just appears at these two addresses, 40, and there's another device at 70. After that, it's basically just installing TensorFlow. TensorFlow is a very popular machine learning framework. Basically what it's good at is matrix multiplication on GPUs, and with neural networks, that's what you're doing a lot of, is a lot of matrix multiplication. There's a driver for the PWM chip, which John talked about extensively, and for the camera. And that's pretty much all the software you need. It's reasonably straightforward. So once the car software is installed, the first thing to do is basically you've got to find it. And this is where we just used MQTT. We wrote a little script that basically gets the host name, the IP address, and basically the time, and basically just puts that together a message and publishes it to test.mosquito.org, which is a public MQTT server. I figured we weren't giving too much away by publishing some random IP addresses. So you basically can use the command mosquito sub, which subscribes to the topic OHMC, and that OHMC hash is basically a wildcard of all the topics our cars publish to, and you'll see a message that looks a bit like that.
The hash?
Yeah. Yeah, okay. Oh, well, we're stupid enough to do anything, so anyway. So basically that's how you find your car, and so it's probably just a handy technique to know. So the first step is to basically test your car to see if the steering and throttle channels around the right way, and you don't get a runaway. And so we recommend you put it up on some convenient I don't know, some roller tape or something. And so once you know your IP address, you can SSH into the Raspberry Pi. So it's using username Pi and password of Raspberry. You see to a directory called OHMC car, and you just type the command Python manage drive. So all of the donkey car code that is used for driving and training is in this Python module, Python script called manage. And you can basically see that it'll produce some error messages, which aren't here. So if you see some warning messages, one person pointed out that they thought there was a problem, but there's not. You basically...
Andy, just,
sure.
Could you just clarify?
Yep.
In this example, it says Robocar, and above it says IHMC car. So could you just explain the different cars?
Oh, okay. Sure. Well, you covered plan A, B, and C electronics to some extent?
To some extent.
To some extent, okay. I left the plan. Basically, John Spencer worked very hard on our plan A electronics, and one of the problems about hardware and lead times is sourcing components. And the Chinese factory that was assembling them took a long time to get the foreign components, but also the Chinese source components. And at the end, we had to make a call about whether we were going to get that board done in time for the workshop. And so what we thought it wasn't going to happen. The other thing we did was you need to be able to develop software at the same time as you're developing hardware. So often, and I don't mean this as a slight to the hardware engineers, but if you've got a delivery date, often they go, oh, as long as we get the hardware done by that date, we're good. But that leaves you no time for software development. And it just happens so often, in volunteer projects, it's completely understanding, but it also happens I've seen it so often in commercial projects as well. So planning around getting that hardware done early, and then having prototypes like this car, which we basically just took a Raspberry Pi, an Adafruit PDM servo driver, bolted together with a USB brick, allowed us to get underway with the software. But also the problem with this, though, is it disguises problems. The USB brick goes for hours on end. It's also decoupled from the battery that's driving the motors. And this is quite different from the final design. And so well, I'll talk about this problem in a sec, but basically we had issues around knowing whether the power supply and battery was going to be good enough to run the workshop. But anyway, go back to source component timing. So we didn't know whether the factory would deliver on time. But quite often, if you have a good relationship with the factory, you can ask them to prioritise or source components from other places. So we tried that. That was where Cameron Leeson, again, being in Shenzhen, just being a short drive or phone call from or WeChat from the factory, was continually trying to update us and let us know until in the end we just had to make a call and say, no, not going to make it. And that's when John did this extraordinary effort with what we call Plan C, which is the third board. So yeah, so that's one thing about hardware. It just takes so long to turn things around compared to software. So anyway,
the one way you often put it is that it's like you have a compile time of a month instead of a few minutes.
Yeah, which is why people go to Shenzhen. We basically have a compile time of 24 hours, which is pretty awesome. Okay, so but just quickly on that problem about the power supply. Yeah, sorry, jump in, please. Yes, there's still fabrication places in Australia, but one we used in Carrum is just shut up the other month. So it doesn't matter how much money you've got, if there's enough business for these places, they do shut down.
So that question for those who are further back was, if money was no object and you needed to get this done in a hurry in Australia, is there somewhere you could go and get this done?
Yeah, and the answer is yeah. Was it PCB Zone? Yeah, we've used them. They're great.
You still need to get all the components.
Yeah, so you still have the part sourcing issue as well. Yeah.
Yes, and there's a lot of factories use DigiKey and Mouser, and what's the other one? LTSC, a big Chinese one. Anyway, yeah. But which was it? Yeah, but these are. But what it comes down to is you pretty much turn. Basically, you will do board design, turn that around, and then populate that yourself as a prototype, and then pretty much then go straight to Chinese factories as a go-to market usually. Yeah. So the problem with prototyping that's not realistic, it doesn't represent your production machine, is that with the decoupled batteries here, this machine ran fine, and then when we got into last week and we're testing out John's Plan C board, it didn't run fine. We're watching the voltmeter go 8 volts, 7.9, 7.8. We're going almost that fast, and we were scared. And actually, after some testing, it turned out to be we need to cycle the batteries a few times so that they hold their voltage. But yeah, it was a little bit of a scary
I was
moment.
panicking just a bit.
A lot. Anyway, back to the software. So the Donkey Car software will basically load its configuration. So there's a file called config.py, which I'll chat about in a sec. Checks the camera's good, loads up the web server, and after that you'll see, this is the key message to look for, that there's a web address that you can now go to with your browser to control your car. And once that comes up, and I should actually just do that now so we can see it. So let's.
This is one of the places you do substitute the numbers.
Ah, yes. Let's get this going. So yes, 310. I'll do. So that'll start up, and so you can see it's bringing up Donkey Car, and I'll just go back. They're the errors you can ignore. They're just TensorFlow errors, runtime warnings, just about version numbers, really.
So first to get to the web page control of your car?
Yeah, absolutely. Yeah, go for it. The ESC is turned off.
Here it comes.
Yeah, no.
Address in 3, 2.
There we go.
1.
Just to make it fun and fair for everyone. It's but not only is it turned off, but the battery is disconnected. There we go. So, There you go. So, well, have a go. That's the address.
Who's going to get there first?
There we go. So there's the carpet. So what you do
Whoever gets control, go for Tim.
here we go. That's me.
Yes.
Anyway, so that's how you drive it. Yep, someone's got it. Awesome. You basically have to go back to the neutral, and then go back. Yeah. All right. Where's it? Yeah. All right. Anyway. Yeah. Anyway, so that's how you can drive around. The idea is you basically get a bit of practice on the track so you can drive around smoothly, so it learns how to drive well rather than poorly. Yep. So actually, I should leave the monitor up so you can see what's going on. On a mobile phone, which I think I've got one here. No. On a mobile phone, you get the same interface, and what you can do is you can control the car by just going left and right, forward and backwards. And I find for training, it's much better to control the car that way because you can follow behind the car and do much more accurate steering. And also there's a when you have the mobile phone, you have to click the start/stop vehicle button because it's much easier to get out of control of the phone jiggling around. So you basically have to deliberately do that. So once you yeah, keep going. Literally tap dancing. So another thing you don't have to do, but is good, is you basically do steering and throttle calibration. So what that looks like is, I'll just put this in the background. Maybe that wasn't a good idea to put that in the background. In your configuration.py file, you've basically got things like the camera resolution, which is 120 by 160 pixels. It's only a Raspberry Pi, it's not very powerful, so we keep the number of pixels low because that directly affects the number of neurons in the network and the amount of mass the machine has to do. The frame rate is 10 frames a second. On my machine, the stereo channel is 1, and there's the PWM limits. So 480 is full left, 280 is full right, and about 400's in the middle, 380's in the middle, and also the throttle. So the throttle is round right down. 425 is not a very big number. You could have that at 500, and this thing will probably be doing, going basically chasing Lime scooters down the street, if it's properly trained.
So there is a calibration process you can do where you put the car against a wall, have it turn, and see how much of a circle, like turning circle it is, and you can use that for calibrating those values so that the behaviour of the car becomes more predictable.
Yeah. No, not at the moment.
Unfortunately, no.
Yeah.
The question was, is the battery voltage connected to any input? Monitoring battery voltage would be a really neat idea, yes.
So the last couple of parameters are about training. So in neural network training, basically we have what's called an epoch, which is basically a run of training where before you check the loss value and adjust the weights. The batch size of 128 means it's going to do 128 images and per batch and train on those. And basically there's the training split. So there's what's called the training set. So 80% of our image is going to be used for training the network, and 20% of the image is going to be not used to train the network. It's going to be checked the network to make sure it's not overfitting. So it's basically not learning to do just exactly this track and can never do any other track. So that's the configuration. So let's get out of there. Oops, definitely don't want to write that. Okay, so I think you're fairly stuck. Here we go.
Since we're looking at this video feed, I think it's time for you to tell a story about what you saw through the video feed while you were doing some early testing.
Yeah, so I was in basically some shared flats for a while, and so there's a driveway where I was sitting inside just training up and down the driveway, and
so you were inside just watching the video feed. You
Yes.
couldn't actually see the car.
No, not at all. And some new neighbours just moved in. They had a 2-ton RV, and the last thing I saw was this car tyre basically on the last video frame. I should have prepared better because I've still got it. But basically, I went racing out of the house going, what have you done? And my neighbours are like, well, what have we done? And I was like, you've just run over my car. And they're like, what car? And anyway, so they were very nice. They're very apologetic, and it really is my fault. But what happened was with the wheels, because it was staccato, the four wheels were strong enough to support the weight of the car with the RV, and basically the suspension had pushed down the electronics. And so basically what I had was a Raspberry Pi, a very flat GPIO pin. So basically the car died immediately. But when and it cracked all the acrylic, but we basically laser cut some new acrylic, straightened all the pins, and the car drove again. So it's now called plant. No, they went straight over it. So it's kind of got car tracks down the Raspberry Pi. I'll find a photo for you later. I'll post to LCA chat. It's pretty amusing. Yeah, it's pretty cool. Anyway, but let's just try and get this back on track a little bit. So what you want to do is then acquire data. So we can actually acquire some data if you want. All you got to do is keep driving. We'll just go start recording. So you're now training to training. And while that's happening, you'll basically see in here there's a directory called tub. And if we just look in tub, that's 10 images a second being recorded. And further down there's there'll be the steering and throttle values. So basically that's what's being recorded.
So it can correlate what the steering and throttle values were at the time each of those frames was captured.
So for those of you who've got these cars, basically get it set up. We've got some tracks for later in the week, and you can be able to drive around with a setting like that. Then once you've got that data, you will then want to basically upload it to your laptop, because the Raspberry Pi is not really fast enough to train. So just basically just do an SCP command. Just move the hub up to your host. I always throw the date in there because I like to keep all my training data based on the date. And after that, you use your laptop to train the network. So how we do that is we basically just bring up our Python virtual environment, cd to the directory where our data is, and just run the command manage.py train. It's the tub of all the data in it, and it's basically going to produce a model. So I'll just quick diversion on neural networks. When we hand code, it's going nuts here. When we hand code, basically we write functions, and functions have inputs and they produce an output, and we spend lots of time writing the lines of code that join the two together. And pretty much anything can be used as input. In this case, images or financial data and so on. And the idea is to produce an output. In this case, we're taking an image and we're producing two numbers, which is what should the steering value be, left or right or something else, and what should what throttle value be. And what a neural network does is, instead of writing lines of code, it's basically got a large number of cells which are connected in layers. So basically, in this machine, it's about a 15-layer neural network. The number of neurons in the first layer basically corresponds to the number of pixels. So there's 120 times 160 neurons in this first layer. And then layer after layer, basically, its job is basically to reduce the number of parameters until you finally end up at the bottom of the 15-layer network with just two parameters, a number for steering, maybe say between -1 and 1. And the way this works is the mass that connects to each of these layers is basically have what's called a weight. So basically take the output of so in a fully connected network, you have the outputs of all the neurons connected to the input of the next layer, and you have some weights that say how much to ascribe to each value. And so the training process basically says, right, let's run this image through the network, produces a rubbish value because the network's not very trained, and you basically say, what's the difference between what the actual value, steering value, which was go left, to the predictive value, which might have been go right. Well, that's pretty bad. And so that difference is called the loss. And then for a process called backpropagation, which is basically the neural network adjusts the weights of the network to basically try and move us slightly closer to the actual value. And that's repeated over and over again. Which is why we use GPUs, because you might need teraflops to do this. And over a period of training runs, you'll hopefully reduce that loss. And I'll show you. Actually, I can show you this now. In this training run, it's basically saying the loss started off as 58. We ran a step, and now the loss has been reduced to 57, which is it means the predictions are slightly better, and just keeps doing this process until it's not making any improvement. And the idea being that that function, which is basically take this image and produce a steering value, should work for a wide range of images. Where we've seen it, like just today, not go very well is last night I trained the car at night with all the fluorescent lights on, and it was going around the track really well, both the large and small track. In fact, we used the small track training weights, and it drove around the large track quite well. This morning, tried around the track, and it was rubbish. And what happened was we turned the lights off so we could see the projector, and just that change in lighting conditions meant it was no longer producing great predictions. One thing could have done was basically now train using that different light value, and hopefully the car would perform well in both light and dark conditions. So that's the sort of part of the art and craft of machine learning. Yeah. So moving on, because there's not much more time. So once you've captured that training data, you'll just end up with a file called, or is it just model.hdf5, which hdf5 is just a Python format for storing data. And the penultimate step is just to copy that model back to the Raspberry Pi, because the car is self-sufficient. And the ultimate step is basically just to run this command, the manage command again, drive, except this time we're giving it a model parameter. And let's see if we can quickly do that. So I'm going to take control of the car again.
This can only end well.
No, well, given there's no track on the floor, it's not going to end. If you want to, yeah. Yeah, doing SCP commands is pretty unsophisticated. You could use rsync or whatever you like, really. Let's see, so let's look for drive. Okay, so if I just go, yeah, that should be good fun. Let's see how it goes. So it's just really the same as before. It's just loading up Donkey Car, so you've got the web interface to drive it, except now it has a model loaded, and we can then say to the car, now use the model for driving. We'll see, try and demonstrate that a little bit.
Yeah, you're running with a separate battery pack.
Yeah. Yeah. My sole goal is for my car to beat your car.
Short answer is yes. So for those that couldn't hear the question, Mark was saying that on this particular car, the Raspberry Pi is powered by the USB power brick. And do we have any issues with voltage tipping as the ESC powers up? So we have seen some issues. And part of once again, one of the trade-offs that we made was that partly for transport purposes, we didn't want to have to turn up with 32 big LiPo batteries. We got nickel metal hydride batteries with these chassis. So something you can do once you get home is replace the battery with something with a bit more capacity. The only thing is to just check the voltage rating on the ESC. There's a sticker on this little chassis that says that it's rated to 7.2 volts or whatever it is for a nickel metal hydride. But basically this platform is ripe for hacking. You can add a better battery pack, give it longer run time and do that sort of thing. But what we were aiming for here was something which is a good starting point that you can then build on. Yeah, there's a little jumper on the top of the ESC. There is a battery mode jumper. I can't actually remember what that does, but yeah, have a look at the specs for it.
Well, given the nickel metal hydride battery starts off at about 8.2 volts, and it hasn't killed the car yet, I'm not overly concerned. But yeah, take some care. Oh, yeah, sure, yeah, okay. So the last thing I just really show you here is that the car is currently in user mode, where basically I would control the steering and angle. You can see if you can influence the car. And we can put it into local angle, which is an obscure way of saying the AI is now controlling the wheels. So it's trying to make sense of the ceiling at the moment.
So local is the device itself. So local is the car from the point of view.
What we can do.
And angle is steering angle.
So hopefully what happens is if looking at that line, it might, well, actually, someone can just drive it around if you like. I'm going to try an experiment.
Here comes the tape.
Oh, awesome. If you bring the demo over here, please. Okay, let's see how we do. So So the idea is that you control the throttle and the car's going to go where it's going to go. That didn't work very well. Let's see if this works. Given this hasn't been trained on mottled coloured floors. No, it's all cool. Let's basically lay down some tape. Why am I nervous? Do not turn your back in the jungle. Yeah. So you're just controlling the steering at the moment, or sorry, just controlling the throttle. So just use the yeah. So basically, it's in local angle. So what you should be able to do is just hit the Y key with a bit of luck. Start vehicle. Yeah, it turned by itself? Yeah, cool. It wasn't trained on that surface. Yeah. So just use the I button just very slowly just to bring the speed up a bit. Yeah, well, it made a bit of an attempt, but the idea is that I should be able to, yeah, okay, it's gone mad. Anyway, the other thing you can do is you can basically go to full local pilot, which means you'll be trying to control the throttle and the steering. So I guess it's probably time to wrap up. Yep. But we're at the student dorms, and there's a common room there. We've got kilos of tape. we went over baggage limit on tape. So we'll probably set up some tracks during the week. Maybe put together a BOF at the end of the week. We'll mail out in the mail list. But we sincerely would like everyone to go home with their car self-driving in some respect, because it's up to your imagination as to what you train it on. We obviously we're training it on lines of tape on the floor, but there's no reason not to try and train it on recognising other things, because basically
chase the cat.
Yeah, someone wants to chase their cat. I'm glad I'm not that cat. But yeah, please just grab us any time during the week, and we'd love to try and get your cars going for sure. So my last thought is the reason why I was interested in doing this is it's obvious that for years that most hardware doesn't do much without software, and then just chatting with VC people who invest specifically in hardware, they do want to invest in hardware, but they're not really interested unless there's also some software, some secret sauce that give them a business value or some proposition that scales. And more they're looking towards AI as a measure of that secret sauce. So we're very keen to be doing open hardware, but try and I guess follow what appears to be an emerging trend, and encourage everyone to do the same. And it's also just a whole lot of fun, really. So yeah.
Great. Thank you very much, Andy.
Thank you.